All right, so yesterday we learned the introduction to vectors, what they are, and how we kind of quantify them. All right, we had a couple different ways to name it. So here, if I have the points PQ, I can say vector PQ or directed line segment PQ like this. I can also name it using a bold lowercase letter. Okay, most of the time, if we're just dealing with one vector, it's just V, and it's bold, okay, lowercase and bold. If you're dealing with more, we have, U and W, like I said yesterday. All right. We also learned that we can find the magnitude, which means the length of the line. And that is denoted with two absolute value signs on the outside, right? And then we can find that using our good old-fashioned distance formula. And then we can also find the direction. There we go. By finding the slope. All right, that tells us where we're pointing. So we saw that we can say that two vectors are equivalent if they have the same magnitude and slope. All right, so vectors u and v are equivalent if they have the same magnitude and direction. Okay, so that's all recap. Let me see. We like to be, so when we're dealing with vectors, vectors can literally be anywhere, right? Depending on where our initial starting point is, and then depending on, which direction and the magnitude. If we're talking about a vector in the coordinate plane, right, it can be anywhere. I can have, which, if we're dealing with a lot of vectors, can get out of hand pretty quickly. All right, so, here we have vector v, here we have u, here we have w. And maybe I want to do some operations on these or just compare them. And it's hard to do that when they're all over the place. We can have a vector in what's called standard position. When its initial point is the origin, right? So we can move our vectors around where we need to, and dealing with geometry and translations, we're not changing the size or the direction, we're just changing its position so it looks nicer to us. So we're more it's easier to deal with it when it's in standard position. So and again, just remember the P here, or where the dot is our initial point, and then where the arrow is, remember we call that the terminal point. All right, so when we move the initial point to the origin, then we say that that vector is in standard position. All right, so here we have Now, one of the reasons we like to deal with standard position is because it removes that, that randomness, or, wherever that initial point is, it makes it 0, 0. So that makes things easier for us, because then for, finding the slope and the magnitude, you don't have to deal with two coordinates. You really only have to deal with one coordinate, and that's where the terminal point is. So, with a vector in standard position, okay, then, like I said, all we have to worry about is its terminal points. And then when we're comparing two or more vectors, well, if they have the same terminal point, then that's all automatically telling you that they're equivalent, right? If you move the initial point to the same spot, and the terminal point also ends up in the same spot, then right away, without doing any extra work, you can tell that they are equivalent. So that terminal point, we give it a new name. Okay, and instead of using x and y, we say it's v1 and v2. All right, so this point here would be v1 and v2. And it depends on our vector, right? For vector v, it's v1, v2. For vector u, it would be u1, u2. Okay, so then we have something called the component form. Okay, so when we have it in vector form, we represent it a little differently. And we don't use those rounded parentheses anymore. We use the triangular brackets. All right, so the component form of the vector v is written v equals bracket v1 comma v2. Right, and this is what we use to do that comparison. Right, so we can find the component form. So with our original vector, PQ, so we have point P at P1, P2, and terminal point Q at Q1, Q2, then we can change it. So I can say that PQ would be the difference in your x coordinates and the difference in your y coordinates. Okay, so all of these are equivalent. So it's real simple to find the vector form. You're just going to subtract the coordinates of your initial and your terminal points. All right. So the magnitude Okay, we still use the same symbol for the magnitude. We do the double absolute value sign, right? But now I just have the v in the inside. So originally, okay, if I had two coordinates using the p and q, right, it would look similar to the distance formula. I have q1 minus p1 squared plus q2 minus p2 squared. But if we have this vector form, if I already calculated v1 and v2, then that's just v1 squared plus v2 squared. All right, so now we have a way to make it a little easier for us. All right, so if I had some vector here, I could find the component form by subtracting the coordinates here, and maybe it would go like this. Let me fix that a little bit. All right, and I can calculate everything just using this line now. So, oops, I don't want to remove that. We do have a special condition. Two special conditions. If we find out that the magnitude of your vector is 1, then we call that a unit vector. And if it's 0, well, then we say if the magnitude of v is 0, if and only if v is the 0 vector. And that would just be a bold 0. All right, so we got a few minutes left, and I've been giving you kind of a lot of definitions and rules. Let's take a look at some numbers, some examples. All right, so we want to find the component form and magnitude of vector v if its initial point is 4, 7, and its terminal point is -1, 5. Vector. That's an O. Vector. Okay. So just to kind of give you a feel, I'll sketch it out. It'll be a crummy sketch, but you get the idea. So my initial point is at 4, 7. I gotta go up to 7. 1, 2, 3, 4, 5, 6, 7. 4, 7. So my initial point would be up here, and then -1, 5 would be my terminal point. All right, so that's it in its original position. So we're going to move it down. So it's got the same direction and magnitude, but now it's going to be down here. So that's what we're trying to find. What is this point here, which would be V1 and V2. All right, so just to keep with what we have here, the initial point we'll say P, which we had P1 and P2. That's going to be 4, 7. And our terminal point Q, which is Q1 and Q2, is -1 and 5. So for the component form, right, I'm going to find each one of these separately. So V1 is the difference in my Q1 and P1. So -1 minus 4 gives me -5. My V2 is the difference in my second coordinates. So that's going to be 5. Oops. Let me write it out. Q2 minus P2. 5 minus 7, which is -2. All right, so if I plotted these points down here, now I have -5, -2. All right, and this was just a sketch, so I didn't, this isn't accurate. But if I counted 5 to the left and 2 down, I'd have an equivalent vector. Oh, wait. Oh, I did something wrong, but it's okay. All right. So now for the magnitude, we already kind of got it set up. Okay, I'm just using these numbers now, and I don't have to do the whole subtraction part. I don't have to do the whole distance formula because I already subtracted here. All right, so it's just going to be -5 squared plus -2 squared. And just be careful. Remember, we always get a positive when we square. So the magnitude is the square root of 29. And again, we're going to leave it just like that. If you can take the square root, so if there's the square root of 36, then you'd have 6. But if it's not a nice square root, don't even worry about simplifying it. Just leave it as the square root of whatever we have. All right. Any questions about that? I think that's pretty straightforward. I know it's a lot of, vocabulary and new ways to name things, but it's subtraction and the distance formula. So I think that's pretty simple. All right. Any questions? All right, give me 1 second. I'm going to stop recording. We're done with the lesson, but just hang on for a minute.